I don't even know. All right. So, yesterday, we left off here, and we said in a reaction mechanism containing a catalyst, the concentration, and the Jawa didn't like that, of the catalyst is unchanged. However, the catalyst will sometimes be consumed in the rate determining step, only to be reformed in a later step of the mechanism. What does this look like? Flip it. So, here is what this looks like. So in organic chemistry, a specific class of compound called a ketone, bless you, can be converted to another class of compound called an enol. All right, so this is a ketone going to an enol. Not super important. It's found that the rate of this conversion can be changed in the introduction of another substance. The chemical equation showing two examples of the introduction of such substances are given below. So here, that's hydronium, yes. I have H3O in the beginning, and I also have H3O at the end. So that's a catalyst. That's how you know if it's a catalyst. Also, you can also use hydroxide. So here, I have hydroxide at the beginning, and then I have hydroxide at the end.
Is that middle step the
That's the intermediate step.
fancy one that you said that exists for?
Yes. So H3O and OH both increase the rate of the conversion. Identify the role. Those are catalysts. How do you know? Because you start and end with it. That is how you identify a catalyst. What features of the equations are support your answers? Because you start and end with it. I gave you the answer. You start and end with it. So, there are a couple different types of catalysts we're going to talk about now. First one is a surface catalyst. This is usually a metal, which is a solid, reacting with a non-metal, which is usually going to be a gas, not a liquid, because that doesn't really make sense. Or the catalyst is going to be in a different phase than the reactants. In a different phase than the reactants. So, an example would be hydrogen and nitrogen gas is absorbed onto metal, and the covalent bonds are weakened, producing highly reactive, it's kind of cool, singular nitrogen and singular hydrogen atom intermediates. You can see why that would be highly reactive, right? Because hydrogen and nitrogen, first of all, never want to be by themselves, right? Those then react very quickly to form NH3.
Does it matter what the metal is, or just that there is a metal?
There's a metal. Putting the gases onto a metal surface also increases their concentration, causing more collisions and a faster reaction. So, if you flip the page, this is what a catalytic converter is in a car. So, if you flip it, this is why people steal it. They do steal these. Catalytic converters contain transition metal catalysts embedded on a solid phase support. The solid phase catalyst comes into contact with the gases from the exhaust, increasing the rate of reactions to form less toxic products from pollutants, such as carbon monoxide and unburnt fuel. So that's why people steal catalytic converters, because they have transition metals in them, worth money. So transition metals reacting with monomers, if you do that, you've made plastic. That's plastic. So, enzymes. This should look like biology, right? Okay. Complex protein molecules. Don't worry, you're not going to be doing a lot of biology here. And I said ew, because I feel the same. That act as biological catalysts. So an enzyme is a complex protein molecules that act as biological catalysts. Many times thought as a lock and key. No. I know. Ugh. But it is. All right. It's a lock and key. What? Protein. Yeah, it's protein. Speaking of lock and key, I just got my new suitcase last night. So my carry-on suitcase that I had since I was in high school died when I went to Salt Lake City last year. As I was in the airport at Cleveland, going down the stairs, the wheel broke off. So I had to drag my suitcase or carry it all the way through Cleveland, all the way through Denver, all the way through Salt Lake City, and then all the way back. So I got an Away suitcase. And Away is like a very nice brand. I paid more money for it, but it's very high quality.
Like, I thought your suitcase was like yours, it's gonna bust over.
That's what I
No,
was thinking.
no, I couldn't wheel it. And if you have a suitcase that doesn't wheel, that's literally just like a box. So, yeah.
Might as well bring a cardboard box with you.
Seriously, it might as well have been a cardboard box. Anyways, how do we get on that? Oh, lock and key. Oh yeah, the new thing's sweet. It's like the zippers. The zippers on this case lock in. It's like the zippers, they turn and then they go in the lock, and that's how it locks. It's really cool. It's really cool. This accelerates the reaction by connecting to the reactants and either aligning. Why is he talking about Taco Bell? Either aligning or causing the reactants to react with a lower activation energy. So here's my enzyme, here's my substrate, here's them together. It goes in here and then it rips apart, makes the products. Doesn't Mr. Conrad do like a stop motion project on this? Yeah. So let's keep going. The sequence of elementary steps that make up a chemical reaction is known as the mechanism. So we're going to look at these mechanisms. Known as the mechanism. Each step will be either fast or slow. But, the overall rate, this is really important, put a star by this. The overall rate of the reaction is only dependent on what do you think? No. Only dependent on you have one choice, fast or slow.
Slow.
It's only dependent on the slow step. Why? Cross-country runners, right? It's only based off of, your score is really based off of the slowest person on the team, right? Essentially.
I would know. I would know.
So, it's the slowest thing in the equation as well. So, the slowest step determines the rate.
Well, the slowest of the top 7.
Right. Right at the top 7. You got it.
Oh, okay.
So-
It's not the fastest that turns.
Correct.
Okay.
To determine the rate, it has to be the slow step. That's really important. This step is known as the rate determining step. I know. It's
So
wild.
a cross-country team really isn't a team, it's just like the first 7 people,
Yes.
and then everyone else.
Yep.
Well, everyone else is still
Well,
running.
it's still a team, dude.
Yeah.
But the other people don't do anything if it's only the team
Okay.
of the
You
first
just said like
Wow.
everyone in this room, so.
Well, okay.
Who is,
I am never inviting you to a cross country meet.
wow, who is number 1? Maddie?
Don't break up in front of me.
All right. Yeah, we don't want to see an actual breakup. That'd be ugly. That'd be ugly. All right. All right, so now for the rate equation. So there's an equation that goes with this. So rate equals
What is that?
K
What is that?
times concentration of A to the X times concentration of B to the Y times concentration of C to the Z.
What is that?
K is the rate constant.
Why am I in calculus again?
So now at this point of the year, this is where we start to get tons of Ks. All right? I don't know why, but there's just tons of constants, and they're all K. So just be ready. Oh, look, I said the first of many Ks. See, like I am always literally ahead of myself. So X, Y, and Z are the order. All right, they're the orders. They're the orders with respect to the concentrations, Jaway, symbol, of reactants A, B, and C. The order with respect to a given reactant is the power, which the concentration, I put it in a bracket, so I did it both for you there, Jaway, of that reactant is raised to. Is raised to in the rate equation. The overall order of the reaction is going to be the sum of the individual orders. Rates are only based on reactants. You will never see products in the rate equation. You will never see products. It only depends on what we start with. Only depends on what we start with. Flip the page.
Oh no. There's a lot of blanks.
So, imagine if you had to write all this, though. Rates can only be determined experimentally. So, I don't know why that's such a long word to write. Experimentally. Using coefficients. Using coefficients of the balanced equation will not deduce anything. So, that means orders must be determined experimentally. So you're going to have to actually do an experiment to determine this, or have some kind of data to determine this. And it's not hard, but you have to have some kind of data. It is, but it is possible to get orders from the stoich of the balanced equation. If you know, it is the rate determining step. So if you know what the rate determining step is, you can use the stoich to get your orders. And then the coefficient, I'm going to show you all this in a little bit, in the slow step becomes the power that the concentration is raised to. Note, rate, constant, units get wacky.
It's gonna be like 1.95 or something.
No, that's I'm talking about the units. So it could be like molar squared divided by r cubed type things, like weird stuff. Weird stuff. That's probably the hardest part about this, is determining your units on your rate constant. A reactant that has zero effect on the rate would have an order of what? Zero. Because any number raised to 0 equals 1. If you multiply by something by 1, does it change? No. And therefore it can be what? Omitted, excluded, yes. It can be omitted from the rate equation. Note, orders can be fractional. Yeah, you can have a half order. You can have a half order. In all valid rate laws, the sum of the individual steps must add up. Other note, this is just a lot of stuff I just wanted to tell you before we get to the actual stuff. Other note is intermediates. So here come the intermediates I said we would talk about more later. Are formed in one step, but then are used up in a later step. They're used up in a later step. When an intermediate is found in the rate determining step, it is usually replaced. And I'll show you that in a second. If a substance is present at both the start of a reaction in the same form at the end, we already know that's a what? That's a catalyst. That's a catalyst. So, take a look at the decomposition of hydrogen peroxide.
What is the thing that says after no?
Start. Intermediates.
Oh,
Intermediates are formed in one step and then used up in a later step. So, here we go. Here's step 1. Hydrogen peroxide plus iodine ion gives you water plus iodate. Step 2, iodate plus peroxide yields water plus iodine ion plus oxygen. Overall, 2H2O2 plus 2H2O gives me plus O2. You guys remember this is like Hess's law? How I got that overall? Yes? If I asked you what is the catalyst, what would you say?
Well, no, but it says start and end.
You have to start and end with it in the intermediates, in the little steps. Iodine.
But the iodine's not in the overall.
Right, because it's a catalyst. It wouldn't be in the overall, right?
No.
If you start and end with it, it'll get subtracted out at the end when you would do the Hess's law. Is a catalyst actually part of the reaction? No, it's not. So that's why you have to start and end with it, because when you subtract at the end, they cancel out. Does that make sense? Okay. The intermediate would be what? Any guesses on the intermediate? Well, look at your overall.
So it's gonna be used up, so it's
Iodine?
It's the IO minus. It's the IO minus, because if you look, I end with it in the first step. I begin with it in the second step. That's how you know what the intermediate is. And also the intermediate's not going to be part of the end equation because it's used up immediately.
So neither the intermediate or the catalyst are part.
Correct. So that's how you identify the difference between a catalyst and an intermediate. Catalyst, you start in the first step, you end in the last step. Intermediate, you end it within the first step and begin with it in the next step. So it's actually really easy to identify the difference between a catalyst and an intermediate. Aubrey, are you okay with that?
Yeah.
Okay. All right, last note. A reaction that is second order, I don't believe you, but that's okay, has a rate equation of K times concentration of A, concentration to B. Because A to the first, B to the first, 1 plus 1 equals 2. This could be carried out with a large concentration of one reactant compared to the other. When this happens, the reactant with the large concentration will basically be constant. Basically be constant because its concentration will change so little. It'll change so little compared to the amount of the other concentration changes. So if B is really bigger than A, you could actually rewrite the rate law to say that K just equals A. And it's not a pseudo first order reaction, but you probably won't see that. But I just wanted to kind of put that out there in case. I can see like AP doing something on like a multiple choice, but I don't think you'll see that. But you can't say I didn't say it. So there you go. Yes. Here we go. Identify the catalyst and the intermediate in the mechanism below. Oh shoot, it printed weird again. I hate that. These are supposed to be arrows down here. If you guys want to fix that. Why is he talking about pancakes? Oh, I bet he's talking about the Golgi apparatus. Is that pancakes?
Yeah.
Oh, yeah.
Yeah.
Well, I just started
Dude, like the purple
rewatch
thing.
Cake Boss. I love that show.
Real.
Right? Like every cell.
In physics, we were taking notes on blood.
What'd you put for the cat?
Why was it
And all of a sudden, in the health classroom, we just hear him go, "You know, a lack of sleep harms your immune system."
Okay.
You're the one who's
Vilma.
better than me.
Vilma, what'd you say for your catalyst? Catalyst, you have to start and end with it. So try again.
What are you doing? Look at. Are you a second?
Yes, your catalyst is V2O5, so I'm squaring my catalyst. Maggie, what's your intermediate? What's that? Nope. Intermediate, you have to end within the first step and begin within the second step. Yes. Your intermediate is V2O4.
The vanadium oxides just be.
Yeah. Okay. I hate how this copied because I wish it would have been on the top of this next step, but it's fine. The chemical reaction, W plus Y, gives you Z, has the following sequence of steps. Step 1, W goes to R. That's the slow step. Step 2, R plus Y goes to Q. It's fast. Step 3, Q goes to Z is also fast. Flip the page. This is going to be annoying flipping the page. Here, we're going to flip back and forth. The rate only depends on the concentration of what?
Slow. Wait.
The rate only depends, but it's going to be only in which part of the slow step. It only depends on the concentration of what? W, because W is the reactant, right? It only depends on the concentration of W, since it's the only what? Reactant. Since it's the only reactant in the rate determining step. So the rate equation would be what? Rate equals K times the concentration of W. You got it. So the order with respect to W is 1. Yes.
Okay, wait. What's the? I don't understand the order thing.
The order, well, it's W to the first. So if there's no exponent, there's a 1 there, right?
When would there be an exponent if it was like?
Stay with me. Stay with me. Stay with me. Okay? Example 2. The chemical reaction A plus B yields C plus D has the following sequence of steps. Step 1, A This should be equilibrium. This did not copyright.
What is fast equilibrium?
All right. So that there should be really an arrow going both ways on that.
Is fast equilibrium on? Does it like just reach equilibrium quickly?
It just says it's the fast step, and it's at equilibrium. And then I have step 2, Q plus B yields C plus D, not at equilibrium. So the slow step contains what? Q and B, right? So the rate is going to equal K, concentration of Q times the concentration of B. But
Oh no, oh no, oh no.
what's an intermediate, Aubrey? Q is an intermediate, which means its concentration is basically impossible to do what? To calculate, isolate, however you want to say it. So we have to switch Q with something else from that equation. And because Q is in equilibrium, because it's in equilibrium with what? With A, they can be switched. So the rate actually is going to equal K times the concentration of A times the concentration of B. So whenever it's at equilibrium, you can't have an intermediate in your rate law, is what it comes down to. So if you have an intermediate, there's going to be something at equilibrium you're going to have to switch out. Not bad. Example 3. So here we go. Conceptually, rates can be determined pretty easily with a little brain thinking. So here is the equation for this data. BrO3 plus 5Br minus plus 6H plus yields 3Br2 plus 3H2O2, 3H2O liquid. The results of 4 separate experiments, because rates can only be determined experimentally, right, are given in the table below by inspecting the initial rate data. It is possible to determine the rate equation. And since the rate equation and the mechanism are linked, to deduce information from the mechanism. I'm trying to think how I want to do this. Is it the same one on the second? Is this like a repeat? Yes. All right, flip the page. Flip the page. So I can do this by inspection. If I'm doing it by inspection, other concentrations are going to have to be held what? Constant. So I have to keep something the same. So let's compare the results of mixture A and B. In mixture A and B, doubling what? The concentration of what? Let's do BrO3. Doubling the concentration of BrO3 minus. So this is doubled, right? Everything else is staying constant. Agreed? What'd that do to my rate? I doubled this. These are constant. What happened to my rate? That doubled the rate. Therefore, the concentration of BrO3 would be what order?
Second? Or no? Just
It would be first order, right?
why is doubling first order?
Because it would be like this times 2, right? Or this times 2 is equal to this times 2. So it's going to be first order.
It was like if you doubled the concentration and the rate went by 4, would that be second?
That'd be second order, right? You'd have to quadruple to make it a second order.
Yes.
The other one. Comparing the results from mixtures B and C. So now I'm on B and C. So BrO3 stays constant. This stays constant.
Doubled the rate.
Doubling the concentration of Br minus did what to my rate? Doubled the rate. So therefore, the rate of Br minus is said to be first order. First order. Comparing the results of C and D. So Br stays constant. This stays constant. Here we go. Doubling the concentration of H plus does what to my rate? Quadruples the rate. Therefore, the rate of H plus is said to be that second order.
Would you have to like multiply by like 9 or like cube it to get a third order?
You won't.
Okay.
Because remember, third is like, it's very, very, very rare to have
Wait,
something like
it's a
that.
really dumb question, but I'm not seeing like the doubling going on.
So on C and D, or anywhere.
Just like any of them.
All right, so A and B. So for A and B, concentration of Br is staying constant. Concentration of H is staying constant. This is doubling. My concentration, 0.05 to 0.010.
Oh, okay.
And that doubles. On B and C, this stays constant, this stays constant, that's doubling, making that double. And then on C and D, constant, constant, this doubles, but this quadruples, making it second order. Cool? Okay. Thank you for asking that question. So therefore, the rate equation is going to be rate equals Ka times the concentration of BrO3 minus times the concentration of Br minus. Now we're using real things instead of like ABC. Times the concentration of H plus squared. Because it's second order, right? Yeah, so that'd be like fourth order overall. We don't care about that right now. So now I would say solve for K. I would say solve for K. This is where it gets wacky. So when I'm solving for K, you just pick any one of these and sub in numbers, because it'll be the same for all of them. So let's do it. Let's just use the first equation. You guys cool with that? Yes? So if I use the first equation, my rate is going to be 10. It's going to be 10, right? Molar per what? Per time.
What?
Well, that's what it says. It says molar per unit time.
Ew.
Are you for real?
Yes. I told you it gets wacky.
Already wacky.
That is equal to K, which is what I'm solving for, times the concentration of BrO3, which is, in the first, we're doing just letter A. 0.005, and make sure you leave units, because units are important here. Times concentration of Br, which is going to be 0.025 molar, times the concentration of H, which is going to be 0.030 molar squared. Agreed? So that means now you have to solve for K. Let's solve for K. See what you guys get.
Why? What sort of
With the correct units.
magic is?
You don't have your phone? For real?
Yes.
Your phone in your locker?
Just so there's 2 periods.
That's crazy.
I forgot my calculator.
Where did you get it?
It's a big number.
You're dividing by a lot of very small.
It's like 2.67 million.
I don't think. Are we sure?
You got 2.6 million?
Oh, wait, hold on.
'Cause that's wrong.
You did.
Yeah, I forgot to square.
That's making it even bigger.
I got all 8s.
It's all 8s. It's literally just all 8s. What sort of?
That's what I got.
That's disgusting. Like that is the worst.
can have my phone back.
Oh. It's
Wait, what?
88 million.
What are sig digs? 2.
So 89 million.
Because what I would have imagined would have been the concentration.
So 89 million.
I got 8.9 times 10 to the 7th. What are your units? This is the part that's important.
So it's molar cubed per time or something?
T to the negative 1,
Okay.
right?
Yeah.
Or we could put per and put T on the bottom. And the negative 3.
For real?
Yeah, because you're dividing, the m is over m to the 4th, so yeah.
Mm-hmm. Because I would take my molar to the 4th, I divide that by my molar, right? A molar divide, yes. Like I said, it's not hard, but the units are just
What
wacky.
does that even like mean? Like a t to the negative? Like what is that? What does that even mean?
Or just a unit. T to the negative 1 is just over time. Just 1 over. So you could have also written that as
Or cube root.
8.9 times 10 to the 7th over T m cubed. That'd be the same thing, right? But I feel like that looks weird. So I usually do negative exponents. I would accept either one. But please write negative exponents. Okay? How much time do we have left?
Or cube root more. Oh, you're like.
Perfect. Because we will end. Yeah, I think this is We're not going to be able to do lab tomorrow, but that's fine. Okay. Here we go. For a reaction between x and y, for the equation below, data has been collected in the table. Deduce the orders of reaction with respect to each reactant, the overall order of the rated reaction, a value for the rate constant, and units of the rate constant. So here we go. 3x plus 2y yields y2x3. So we could do this by what we just did up here again. And this is really what I want you to do. But if you can't like conceptualize that, you can do it with math. You can do it with math. I'm going to show you how to do it with math now. So mathematically, it's M-A-T-H-E. It's not M-A-T-H-A. That's what I lost my 6th grade spelling bee on. And you know what I got after you lost in the spelling bee? A peanut.
Just like a singular peanut.
Yes. My 6th grade teacher, I walked off the stage at Layton, and he's like, here's your peanut in a shell.
That's so good.
It's a peanut.
So odd.
Maybe they're trying to kill you.
I don't know. Well, back then, there wasn't like a lot of like nut allergies that we knew of. This was different. So, yeah. Back in my day. All right, so here we go. How would you do this? So I pick a rate experiment where the rate is bigger than the first one, because I like to divide by larger numbers, divide smaller numbers. You could do it the other way, but then you're gonna have like quarter exponents, which you really don't want to have. So let's do rate 2. So if I start out with rate 2, that's gonna be equal to 4. Agreed? I'm leaving units out till later. That's equal to K times I have concentration of the first thing, which is going to be 0.0100. It's going to be 0.0100 to the x times 0.0250 to the y. That whole thing divided by rate 1, which equals 1, which equals K times the concentration of 0.0500 to the x times the concentration of 0.0250 to the y. So, what cancels out here? Gone, 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 gone. So this is essentially saying that 4 is equal to what?
0.01 x over.
This divided by this is what? 4 is equal to 2x, to the x. Agreed? Yes?
Yeah.
So, x equals what? Yeah.
What?
So that's the other way you can do it mathematically.
So it's because of 4 over 1, right?
Yeah.
And then that equals
Yeah.
0.0, right? 'Cause that
Right.
was-
And then I would do it the same way for the second 2. So I figured out what my first thing is. Now I have to keep the other one constant.
So it's just gonna be the y that changes.
Correct.
So it's gonna be
So I'm going to do rate 1 equals 1 equals K times the concentration of 0.0050. Gotta make sure I don't write this wrong. So 0.00. Wait, is it 0.050 or 0.0? I think I wrote it wrong. Should this have been? It's fine. 0.00500 to the x times 0.0250 to the y. That whole thing over rate what? Rate 3, because I have to keep other thing constant. That's equal to 1, which is equal to K times the concentration of 0.00500 to the x times the concentration of 0.0125 to the y. So on this one, my K is gone, this is gone. So 1, right, is going to be equal to 2 to the y. Agreed? Yes?
Yep.
So y equals what?
0.
0. Y equals 0. Anything to the 0 power is 1. So my rate for this equation, if I just write the rate law, it would be rate equals K times what? Concentration of X to the 2.
Is that 0.0125?
Yes, it's 0.0125. So you can do that with math
So it's just isolating
as well.
X and Y.
Yes, that's it. Just isolate.
It's not that bad.
So you can do it. You can do it like this. Do it like this. Either one I'm okay with. Just show some kind of work. Okay. Go for it. However you want to.
We get used either way.
I don't care how you do it. So, number 1, write the rate law.
If we do it the first way, how do you want us to write it out?
Just show that like something's times something is. I don't care. Just show some kind of work. Write the rate law to give the overall order.
We do not have to solve. Do you want us to solve for K?
3, solve for K.
No.
And I usually do K as a separate step. I'll do the whole math. You guys can decide how you want to do it.
Is it possible to do it the first way when neither of them stays constant?
Why? Something's staying constant. Between 1 and 2, B stays constant.
From 2 to 3.
You can still do it.
Yeah. Okay.
You still can do it. But why are you doing 2 to 3? Why don't you do 1 and 3? Yeah, but look, between 1 and 3 it stays constant. It doesn't necessarily have to be 2 and 3. You could do 1 and 2, then 3 and 1.
On the example, it was A to B, then B to C, then C to D.
Yeah, but this one's not. It's different. You just have to keep A constant in 1 and B constant in 1.
Oh, okay. I get it. What the, like, oh, I guess the-
How do you know which rates to use?
You have to use the rate for the experiments you're using. You have to choose one where you keep A the same. So for
Okay.
for that one I have to use, if I'm solving for B I have to use 1 and 3. If I'm solving for A I have to use 1 and 2. Right?
Does the X and Y's matter? Should I just change those to A and B?
Doesn't matter. You can make those any letters. I don't care what those are.
Alright.
Here's mine. You guys can check yours. It doesn't take a lot of work to show the work. Either way, I'm cool with it. Tomorrow, you need a graphing calculator. So, if you don't have one, borrow one from that teacher. You must have a graphing calculator for tomorrow.
What is the MS? Oh, never mind. I asked my question.